Hello everybody, in this lecture we will be solving 1999 IMO problem number 5. Here is a view of this problem. Two circles G1 and G2 are contained inside a big circle G as shown on this picture, and these two little circles are tangent to G internally at the points M and N respectively. G1 passes through the center of G2 as well. The centers of these three circles, I labeled them as O, O1 and O2 for G, G1 and G2 respectively. The line, and you can clearly see circle G1 passing through center O2 of circle G2. The line passing through the 2 points of intersection, namely these 2 points here, as you can see in the picture, meet the big circle G at the points A and B. We know that line AB is in fact the radical axis of these two circles. The lines MA and MB meet G1 at C and at D respectively. MA intersection G1 is C, and MB intersection G1 again is D. We need to prove that CD is tangent to circle G2. So I did draw a couple of additional lines. First of all, in order to recognize the dilation between circles G1 and G, I did connect M, O1 and O. These points are obviously collinear. And similarly, I did connect N, O2 and O through this dashed line as well. These 3 points are also collinear. Finally, I know that O1, O2, the line segment O1, O2 is perpendicular to the radical axis AB. Now, before I go further, I would like to remind everybody of a very well-known result related to the circle and a chord, and another internal circle centered squeezed between that big circle and the chord. So consider this circle and this chord, and finally another circle, say here, between this big circle and this chord. So these are the two tangencies between the chord, and I can probably name the chord KL, and the tangency points are T, let's call them T1 and T2. And finally, I have a two-step claim. I claim that in any situation like this, I claim that if M is the midpoint of major arc KL, Km is equal to ML, then two results should follow. First, T2, T1, M are collinear, and second of all, I claim that ML squared is simply equal to MT1 times MT2. Let's prove these two results. So let's start with the first one. Why would these 3 points be collinear? The reason is simple. There is a dilation which would take the little circle here to the big circle, and this can clearly be seen by connecting the centers. So that's the center of the big circle, the center of the small circle, let's call it O prime, and the dilation, which takes O prime to O, will also take the bottom point of the little circle, namely T1, to the bottom point to the arc KL, which is M. So therefore, the dilation, and you can clearly see that O prime T1 is perpendicular to KL, and in a similar way, OM is also perpendicular to that same line KL as well. But this result is clearly established by considering the dilation taking the small circle, little circle, centered at O prime to the big circle centered at O. Now for the second part, I will connect some more points here, namely ML, and I would also need, I guess, I think, yeah, I need T2L as well. And let's do some angle chasing. So first of all, I claim that this angle here, namely MT2L, angle MT2L, I claim is equal to KLM, angle KLM. Can you see why? Yeah, the result is obvious because this angle MT2L subtends arc ML, and the other angle KLM subtends arc KM. But from the first part, we know that these two arcs have equal measurement. As a result, these two angles should measure the same. So therefore, it must be the case that the following two triangles are congruent, namely triangle LT1M is not congruent, sorry, I should say similar. LT1M is similar to T2LM, triangle T2LM. Now it is easy to establish the desired result. For instance, For instance, LM to T2M, LM to T2M is equal to T1M to LM, T1M to LM, further implying that LM squared is equal to T1M times T2M as desired. So we have just proved this beautiful result. Just as a quick reminder, if you already have purchased Evan Chan's Euclidean Geometry for Math Olympians book, you would recognize that this lemma is listed as lemma 4.33 in his book, so you can go to as a future reference, go to check for yourself what other properties the circles inscribed in segments have. Okay, so now going back to our problem at hand, I would like to augment the picture like this and start considering how to approach this problem. I would like to start with the following claim. I claim that if I draw the common external tangents to G1, circles G1 and G2, I claim that this common external tangent will go through the point C, and as it is obviously tangent to both circles, and I claim that the other tangent will go through the point D and will be tangent to the second circle as well, so somewhere here I would say. So why would that be? This follows immediately from the lemma that we just mentioned, and consider this this chord. As you can see here, the common tangent, you can consider it as a chord, and it is tangent to our circle at the point C. And if you follow the second part of this, it is clear that all the circles squeezed inside this segment and the circle should have equal powers with respect to the point M, the midpoint of the major arc KL. And it turns out that both the G1 and G2 are squeezed between the big circle G and the chord, which is this common tangency. As a result, MC should go through, in fact, the midpoint of this minor arc. So let me label these points so that we are clear on what I mean here. EF is a chord, and this chord and the big circle squeeze G1 and G2, and as a result the dilation between G1 and big circle G will take C to A, and well, obviously it will take O1 to O, but I claim it will also take C to A, as A is the midpoint of the minor arc EF. The same thing will happen for the line NA. If I connect NA, I claim it will also pass through this tangency point here. But that's a wonderful consequence of this claim that we just this lemma that we have just proved. It works because A is on the radical axis of these two circles, as is B, right? Because it's on the radical axis of these two circles, A has equal powers with respect to both circle G1 and G2. As a result, and also by the fact that G1 and G2 are squeezed, between that chord and the big circle, it must be the case that MCA are collinear, which is given. This collinearity implies, or if and only if, the common external tangent also goes through C, and let's call this point here as, I guess, X here. The same result would imply that AX and are also collinear. So that we have done a significant progress so far. So that was the crux move of this problem. Now next, consider the dilation, which takes, let's call the homotety centered at the point M, which takes the point, well, the circle G1 to G. Obviously this homotety will take the point O1 to O, and it will similarly take the line segment CD to the line segment AB, which simply implies that CD is parallel to AB. But we already know that AB is perpendicular to O1, O2. AB being perpendicular to O1, O2 would imply also that CD will also be perpendicular to O1, O2. So this, the line, if I did draw the line CD, it would have made a 90-degree angle with the line O1, O2. And finally, you can clearly see that O2 is the midpoint of this arc. Let's call these points, I would say I and J. Obviously, O2 is the midpoint of arc IJ, because if you consider circle G1, IJ is a chord of this circle, and I'm connecting O1 to that chord. I'm dropping a perpendicular, and it goes through O2, obviously. As a result, O2 must be the midpoint of this minor arc IJ, but then O2 should also be the midpoint of minor arc CD as well, because CD is parallel to IJ. So let me write that down. O2 is midpoint of arc CD. But now I claim we are done for the following reason. If you consider the angle XCO2, this angle, because of the tangency of EF with the circle G1, this angle is equal in measurement to the angle O2CD. Can you see why? So it is equal in measurement to O2CD by the very reason that I just mentioned a few seconds ago, that O2 is the midpoint of that of the whole arc CD. But then we have an angle bisector CO2 of angle XCD, and the circle, this O2 being the center of that circle, leaves us no choice but a tangency condition such that the circle is squeezed between the two rays CX and C, this tangency point, let's call it Y, the tangency point CY. Clearly, remember that we have already established that CD is perpendicular to O1, O2 as well, and this clearly concludes the problem. So the circle is between these two rays, and CO2 is the angle bisector. We have just proved that these two angles are equal because arc CO2 is equal to arc O2D, as we have explained just a minute ago, and we are done. Hope to see you in our next video.